So last time we studied about the Coulomb's law and how two charges apply forces on each other. What is the amount of force? What is the direction of force? What is the magnitude of force if two charges Q1 and Q2 were separated by a distance? That's what we learned, and we compiled all of those small statements in form of Coulomb's law. This is what we observed. Magnitude of the forces are equal and direction of the forces are in opposite direction. If you increase charge on one particle, forces on both the particle gets increased, and magnitude of forces is equal, opposite in direction. So forces are they are action reaction pair, and the force varies as inverse relation with the distance. That means it follows inverse square law, just like gravitation. Now further ahead, we want to discuss about something called electric field. And for a quite amount of time, it baffled scientists that two charges. How does the second charge Q2 knows about the presence of the first charge? And if you hear about stories about Einstein, even Einstein was baffled by why two magnets attract, why two magnets they repel each other without even touching each other. So it was hypothesized that charge Q1 is releasing something at point A. It has something in this region. It has some effect in this region. Because it doesn't have a mouth, it cannot talk to the second charge. And this something, its effect in this region was given a term named as electric field. So what scientists said that there must be coming something out of the charge Q1 such that other charge can detect its presence. And this whole theoretical concept brought a new insight in this electrostatics. And what they found that this field or this this flow is, they called it field. They called it field, and it was related to electrostatics. So they called it electrostatic field or electric field. Now, this electric field at this point, let us say r distance away, this should be independent of charge Q2. And it must be strong as we go near to the charge. So they formulated a formula to give the value of this electric field. And this was given by force applied when you place a test charge Q0, force applied by Q1 on the test charge divided by the test charge. Now I'm calling Q0 as test charge because test charge should not disturb the original charge. They should be really small. The test charge should not disturb the original charge, original force, original field. If I apply the Coulomb's law here, I will get it as Q1 Q0 by 4 pi epsilon naught into r square divided by Q0. From here, I get the electric field, the magnitude of electric field due to a single charge particle, single point charge. And to remember it simply, electric field due to a single particle or single point charge is given by kq upon r square. Easy result to remember. And as you can see from here, the unit can be written. The Unit of force is Newton, and unit of charge is Coulomb. So unit of electric field will be Newton per Coulomb. And this is how charges know that there are other charges which are present in the region, and there is force acting on the charge. So before going into the properties of the electric field, we'll first do a few problems. And just as you see, if suppose there are two charges, a simple problem will take. If there is a charge Q, and there is a charge another here, and the charge here 4Q. And you want to find a point somewhere between these two charges, where if you keep a third charge, the net force is 0. Okay, so you can directly find the point at which electric field is 0. As you see here, electric field is force per unit charge. So force can be written as charge times the electric field in the region. Force on this particular charge will be equal to charge times the electric field. So if suppose I keep my test charge here at this point A, which is, let us say, x distance away from the first charge. So of course it will be r minus x distance from the second charge. In that case, the field at point A, the electric field at point A should be 0. And we can find the point at which we place the third charge, where net force is 0 or where it will stay in equilibrium. So here at this point, Q will be giving electric field in this side. That will be electric field due to Q. And 4Q, it will be giving electric field in this side. So what you have to understand from here is that if the direction of force on a positive charge is towards left, then direction of electric field is also towards left. It is just like force, but divided by the value of the charge that you keep here. So yeah, you guessed it right. You can apply principle of superposition for electric field also. And you know that electric field due to 4Q should have magnitude equal to electric field due to Q. So this will be 4Q upon x squared equals to Q upon r minus x squared. To solve this, send easy solution. So 4 is equal to x upon r minus x whole square plus minus 2 equals to x upon r minus x. If you solve this, you'll get a value of x is equal to 2r by 3. This electric field due to 4Q, here it should be 4Q upon r minus x whole square. And here it should be x square, because this is electric field due to 4Q. So 4 should be equal to r minus x upon x whole square. From here we get r minus x by x is plus minus 2. And if you calculate here, it will give you x is equal to r by 3. So if you place a third charge over here, you'll get net field as 0 and net force as 0. So just as force, you can apply the principle of superposition in electric field. And we can derive it from principle of superposition of forces. Suppose you want to find the net electric field at point A. So yeah.
Do we have to note down all this?
I'll be sending you the this whole PDF thing, whole thing as PDF. And if you have doubts, you can raise hand and ask me.
Good evening, sir. This is Nihar Soni speaking.
Okay. So next we are starting with principle of superposition, and it simply is think of that Q1 is giving an field. Earlier it was giving force, now it is giving field at this point. And as you know, direction of field will be away from the charge. because if you put a point charge here, direction of force will be away from Q1. Similarly, there is another charge Q2, then you can say it will apply field in this direction. It will have field in this direction. And different charges will apply field, will have field in different directions. But if I apply principle of superposition of forces, net force, if a particle was kept at A, was given as F1 vector plus F2 vector plus F3 vector. And if there are more charges, then you can write it as Fn vector as total sum of n forces. But electric field, as we defined, net electric field will be net force divided by the test charge that you will be keeping here. So it will be F1 by Q naught plus F2 by Q naught. And just to recall that charge is a scalar quantity, we are dividing a vector by a scalar, so it will remain a scalar. And this gives you F1 by Q naught is electric field due to first charge. F2 by Q naught is electric field due to the second charge. And F3 by Q naught is electric field due to third charge. Likewise, up to the electric field due to the nth charge. So we can simply came to this conclusion that net electric field is just the sum of the individual electric fields. Vector sum of individual electric fields. And once we have got these two formulas or these two concepts, we can apply this concept to all types of problems, and the rest all is just mechanics and solving the problems. So starting with the simpler problems first, let us see how charges behave in presence of other charges. Let's start with basic problems. So let us say I have two charges placed on the side of an equilateral triangle. Charges are, let us say, Q, and it's an equilateral triangle of side A. Now, how do I find the net electric field at point A? Question is, find net electric field at point A. So how do we do this? So while making notes, make sure that you're making the question problem and answer diagram differently. It will help you in the revision. It will help you quite a bit. So charge Q, it will give electric field away from it. And if I write the value as E value will be EQ upon KQ upon this distance square. While this charge, it will give electric field in this direction, away from it. Again, same value, so I will just write it as P. Now, at point A, there are two vectors which have angle 60° between them. So, if you apply the concept of vector, the resultant field will be E root 3 at an angle 30° below horizontal. So, net electric field at point A is E root 3. Instead of E root 3, I can write KQ upon A square into root 3. 30° below the horizontal. 30° below the horizontal. So this was just the application of how to apply electric field in different scenarios. We'll do some more complicated problems and we'll learn how to apply the principle of superposition here. Now suppose my charges are arranged like this. This is charge Q, this is charge Q, this is charge minus 2Q. These two are positive charges. And I have to find electric field at point A. I'll use the same concept. I want to write electric field at point A. Take some time and solve it. Try to solve it. It is once you have learned what's the value of electric field, what's the direction, all that is required is just so plus Q. Plus Q will give electric field away from this point. So plus Q will give electric field away from this point. And to mention, this is these are equilateral triangles, two equilateral triangles. So electric field will be away, and the value will be KQ upon A square. For this also, electric field will be E because it is KQ upon A square. But here, see, there is a negative charge. The direction of electric field for a negative charge is towards the negative charge. Because if you place a positive charge here, the positive charge will be attracted towards the negative charge. Value will be 2KQ upon A square. I can write this as 2E. So it is 2E now. And here, the angle between this is 60-degree angle, this 60-degree angle. So this will be 60 degree, this will be 60 degree. So what I can do, I can apply the concepts of vectors. So this is 2E, this is E, this is E. So I will take the component, and component of E along the horizontal will be E cos 60. E cos 60, that is E by 2. And component along this direction will be E sin 60. Similarly, I can take component of this E. This E will again have component of E cos 60 in this direction because this angle is 60 degree. So E cos 60 will be added to E cos 60. So in this direction, we are getting a value of E. E by 2 plus E by 2. And if we take component in this direction, it will be E sin 60. So basically E sin 60 and E sin 60, they will cancel each other out. And we have got one electric field in the left as 2E, another electric field in the right as E. So the net field value will be E. Net field will be E towards the left direction. So net force will be 2, just KQ upon A square, not 2. This is the net electric field. Can be written as 2E minus E, just adding up the vectors. So for point charges like this, it is just a simple technique. You write the value of electric field and you add them like vectors. The resultant vector will give you the direction of net electric field. So here you got an idea on how electric field behaves. We'll make a short note on, yeah.
Sir, how it is 2E on the left side?
Because charge on this is 2Q. Charge on negative charge is 2Q. So 2Q is 2KQ upon A square. I have defined Q upon A square as E. So 2KQ
Yes, sir,
upon A
understood.
square will be 2E. Next, we are going to start with the properties of the electric field. Some properties you have already understood through the problems. See, the first property will be that electric field originates from the positive charge. It originates from the positive charge. And it terminates at the negative charge. So electric field will always start from a positive charge and will always end at a negative charge. Okay, that is the first property. So we write the first property as electric lines of force They originate on positive charge and terminate on negative charge. That is the first property. So if I draw this, a set of positive and negative charge, later we'll see that if there is a equal positive and negative charge separated by a small distance, you call it as a dipole. So electric field which is starting from the positive charge, it will terminate at the negative charge. And these are how we find the electric field lines. Means electric field lines are basically the direction of forces when you keep another point charge. If you keep a point charge here, your force will be tangent to this charge, tangent to this electric field line. Okay, so all these fields, they are showing that direction of forces at each and every point. So suppose you keep a positive charge here at this point, another positive charge Q naught here. It will get attracted towards this line. Means its direction of force on it, direction of electric field will be tangent to this line. Means this force will, this charge will appear will phase will have a force equal to Q naught times E. That is the net force on this charge Q. So second property you can say, right, as the direction of the tangent or tangent drawn at any point on the line of force gives the direction of electric field at that point. Tangent at any point on electric field line gives the direction of net field, net force, gives the direction of net force. Or net field. Now see, if it is giving the direction of net field, then two electric field lines, they can never intersect each other. If suppose there are two electric field lines which are intersecting each other, and you put a charge here, that means it will have two direction of forces. It will have two direction of forces, which is not possible because we have already defined that electric field is direction of net electric field. It cannot have two directions. So third property that we get is two lines of force cannot intersect. Two lines of forces cannot intersect. Because if they intersect, the net field will be in two directions, which is not possible. Next, see, if suppose you have an electric field like this. If electric field lines are parallel, then there is something which is called a uniform electric field. We'll be studying about it later. I'm just introducing the term. Parallel lines means uniform electric field. Means value of E remains constant. Value of E remains constant. E vector remains constant. So if suppose you're placing a conductor is basically a material which has free electrons. If you place a conductor in a field, in an electric field, you'll see that inside the conductor there will be no electric field. Inside the conductor there will be no electric field. Because if there is a field inside a conductor, the electrons inside will move, and electrons inside will keep on moving until and unless the field inside a conductor becomes zero. Okay, so just after some time you turn on the switch to turn on the electric field, the field in this region inside a conductor becomes zero. I'll write my fourth point as the electric field, electric lines of forces, they do not pass through a conductor. Electric field lines do not pass through a conductor. And this is the reason that you can say that positive, this electric field lines terminate at negative charges. So here you will see that negative charges will be accumulated because electric field have to terminate. And while on this region, positive charge will get accumulated because we want charges, electric field line to start from this point. Okay, and this whole process is called induction. We'll be studying about this too. There's a lot of topics in here. This process is called induction. When you keep a conductor inside an electric field region, negative charges and positive charges, they take some definite points. Where electric field lines have to terminate, their negative charges will get accumulated, and where positive charges have to accumulate, the electric field lines they will start. And next property is that electric field lines are continuous. Electric field lines are continuous. Of course, since you have the formula kq upon r square, you will have a continuous field. No breaks in between. It's not like they would suddenly disappear. Okay, they will not suddenly disappear. Of course, they terminate at the negative charge, but besides that, they cannot terminate anywhere. They can terminate at negative charge, they originate at positive charge. Next is more the number of electric field lines in a region, more is the value of electric field. More the number of electric field lines in a region, more is the value of electric field. Now, don't think that electric field line is just this line. It's like something is flowing from this region to this region. Something is originating from this region and it is flowing everywhere in the surrounding. It's not just lines. It is like a flow of water around the region. So to understand this point, more the number of electric field lines in a region, more is the value of electric field. So suppose I have my electric field like this. So I have three regions here. Let me call this as region A, region B, and region C. So electric field lines in this region B, the density is quite less. So electric field at A is definitely greater than electric field at B. And you can see, if you take a cross section like this, in the same amount of cross section, A has the most number of lines. So we can say electric field at point A will be greater than electric field at point C, which will be still greater than electric field at point B. So as the number density of the lines is lesser here, the value of electric field is less here. Okay, these are the points. These are the properties of electric field. Do you have any questions regarding it? So I'll take a few of the problems. You already know how to find electric field due to point charges. What if my charge is distributed in a rod? Let's take this charged rod. It is positively charged. And since charge is distributed in a region, we like to define some new quantities. We would like to define some new quantities. First, I will define something called as charge per unit length. Charge per unit length is defined as, written as lambda. Lambda is just simply charge per unit length dq by dl. It's written as dq by dl. For a small amount of length, dq is the charge on the length dl. Just a notation which we use for our linear bodies, to one-dimensional bodies. Similarly, we will define charge per unit area. Denoted as sigma. Sigma will be charge per unit area. Means if we have a region in which positive charge is distributed, either uniformly or non-uniformly, we can take a small region, let us say this much region. In this much region, if the charge is Q and area of this region is A, you can define sigma. Sigma is charge per unit area. See, this quantity is called linear charge density. Linear charge density. And this quantity is called area charge density. Area charge density. And next you can guess. The third one will be charge per unit volume. Charge per unit volume. Denoted as rho, also known as volume charge density. If you have a small volume and in that volume the amount of charge stored is dq, I will write rho as dq upon dv. All these quantities we will be using in our questions. Here I'll be giving you lambda, and lambda is a constant here. Means for different points, the value of lambda is same. And length of this charged rod is L. What I want to find is the value of electric field at point P, which is, let us say, a distance away from this end. A distance away from this end. Now, what I'm going to do, observe it very carefully. What we're going to do, we are going to use some basic calculus to find the value of electric field at point P. Just as I said, while making notes, draw the question and the answer separately, such that while revising, you won't face any problem. It's a good map. So what I know up till now, I can calculate charge. I can calculate the electric field due to a point charge. I cannot calculate electric field due to a continuous charge just using the Coulomb's law. What I need is the principle of superposition. So I will take a very small portion of this rod, very small portion of this rod. It is so small that it acts like a point charge. And let me take the length of this small region as dl. and such that it contains charge dq. This very small portion of the rod, it has charge dq and length dl, and let us say this point charge is x distance away from P. Now see, you can directly apply Coulomb's law. Due to this charged region, due to this charged length, you can find electric field at point P. Let's call it dE. See, we write delta for finite change. Delta for finite change. But what I want is very small change. Means infinitesimal value of E, infinitesimal change. So I have taken my length as really small, 0.0000 and many zeros, then 1 meter. And luckily we have calculus in our hand, so mathematical techniques will help us in calculating the net electric field at this point. So this very small amount of charge is producing a field at this point P, which is given by dE. Don't worry about dE. dE is just the electric field due to this thing. So it will be K. Your K will be 1 by 4 pi epsilon naught. No issues with that. So K times the charge, value of charge is dQ, whole divided by x square. This was electric field due to this small region or this small length. If I take my charge dQ here, that charge will also give electric field in this direction. If I take my dQ here, that charge will also give electric field in this direction only, in the rightward direction only. So to add up electric field due to all the charges, now electric field is a vector, but all the points are giving electric field in the right direction only in the right direction. So we can just add up electric field due to all the points. In that sense, I can write the net electric field as the integration of this term. So integration is basically adding up. Integration is equivalent to adding up. And adding up infinitesimal changes. And that is why calculus is very helpful to us. The integration of very infinitesimal things is very easy in calculus. So integration of dE is E. And let us see how we can integrate this quantity. K is a constant, I can take it outside the integration. So the constants can be taken outside the integration, but the variables can't be. dQ and x is also a variable. So I need a form in which this can be integrated. X square can only be integrated in terms of x dx. To do that, we'll use this formula. So I can write lambda equals to dq by dl, or let us write this as dx. Lambda is dq by dx, charge per unit length, dq by dx. So d2 can be written as lambda times dx. I can just put dq in here and we'll get a function which depends on x only, lambda dx by x square. As I said earlier, lambda is a constant, so you can take lambda out of the integration. And you know that 1 by x square dx integration will be, that is power of x is -2. So what you do in integration? In integration, we add 1 to the power and divide by the increased power. That will be x to the power -1 by -1 or -1 by x. So integration of this quantity will be k lambda -1 by x. This is the value of integration, k lambda minus x. But there is something that we missed, and that is the limits of integration. Means our charge is limited. It is not going from 0 to infinity. means my first charge from point P was a distance away. The closest charge here was a distance away. And the farthest charge from here, that is L plus a distance away. Closest charge is a distance away. Likewise, adding up all the charges, that means integrating up all the fields. The farthest away charge is L plus a distance away. So what I do here is put my limits. The lower limit is a, the upper limit is a plus L. Lower limit is a, upper limit is a plus L. A to a plus L. Defining also a to a plus L. So this will give you k lambda minus 1 by a plus L. First you put the upper limit, minus sign, then the lower limit. So this is k lambda minus 1 by a plus L plus 1 by a. This will give you k lambda, a minus a gets cancelled, k lambda L divided by a into a plus L. This is the final value of electric field. I know this might seem quite a bit complicated initially only. Later you will get used to it. K lambda L by upon a into a plus L. Where of course k is equal to 1 by 4 by epsilon. So what we used here first is the Coulomb's law, definition of electric field, then principle of superposition and calculus, basic calculus. Now note this down and try to do each step by yourself. Don't just copy each step. You write one step and you try to understand what this step means, how we have got to that step. And if it's not clear, then you raise hand, you ask the questions to me. My goal is to make you understand this. If you can understand this, you will be quite ahead of a lot of students, a lot of competitors. So I have a positively charged ring here. Charge per unit length is lambda. I want to find electric field at point, which is located at the center. When I take this problem, what I can simply do is again same concept. I will take a very small length element. Let us call it, the length is dl. The length of this is dl, and the radius of the circle is given, that is the value r. So this is r, and the positive charge on this can be simply written as lambda times the, if you want to write the charge on this, that is dq, you can write dq as lambda dl. Why? Because my lambda is dq by dl. So dq is lambda times dl. Now this charge will give a field in this region, in this direction. Call it dE. Value of dE is easy to write. dE is equal to k dq upon r square. Okay, but if I take
Sir,
my
A has no charge.
no, A is just a point. We are calculating electric field on it. Point A has no charge. The question is find electric field at point A. So this dq charge, it's applying a field in this direction. But if you take your element somewhere else, the direction of dE will change. Okay, and suppose you want to write dE due to all the elements one by one. So you'll get a region at each and every point from each and every point, DE will be given in the opposite direction at the center. For each point in the left, you'll get an electric field in the right. For each point on the northeast, you'll get an electric field in the southwest. And all these values, they will cancel each other out because electric field is a vector. Okay, so all the components of DE, this will cancel out this will cancel out this will cancel out this. All this component, they will cancel each other out. So net electric field at point A, that is integration of DE vector, it will be 0. So net field at the center, it's 0. Net field at the center is 0. Any questions on this? Here we did not require integration. Integration was just an idea here.
So I did not get the concept of the direction thing.
Okay. So this point, as you know, consider this as a point charge. The point charge will give field in this direction. Is that clear?
Yes, sir.
If you take this point charge here, take element here, it will give field in this direction. If you take charge anywhere else, it will give field in direction opposite to it, away from it. So like this, if you take electric field to all the point charges, it will basically be fields around a point in a circle. And fields are vector quantities. The vector quantities, they tend to cancel each other out if they are in opposite direction and they have equal value. Means
Yes.
DE everywhere will have the same value, K dq upon R square.
Okay, so it will be 0, right?
Yeah,
Because it's cancelled. Okay.
because each direction have a direction, each field has an field which is opposite in direction but equal in magnitude.
Okay, so it's
That's
like a
why
proof.
Yeah.
Okay, sir. Thank you.
Any other questions? If suppose you have a circular ring, the same circular ring you can take. It has charge per unit length as lambda, and you can give it a radius r. Positive charge is distributed here over it, and a small portion of this circle, a small portion of this ring is cut off. Here, a small portion is cut off. Now, this becomes an interesting question because for a small region, electric field will not be cancelled out, but for all the other regions, it will be cancelled out. So how do we approach this problem? And there is a trick to it. Again, we have our principle of superposition to the rescue. I can write this. I can imagine this ring as a sum of two rings. Easy to say, imagine it difficult. Think of it like this. If this is my origin, so I will find this ring as a sum of two rings. This is the first ring and this is the second ring. In the first ring, what happens is I will have a full ring without any cutout section. There's a cutout section. Cutout section, let us say the cutout section has length dl. So if I have this section with no cutout section, I know the electric field due to this. And instead of the circle, full circle, what I will have here is an element of length, call it dl, but the charge over it is minus lambda. Charge per unit length is minus lambda. Means if I superimpose this negative ring, this is my origin, this is my origin. I take this whole section. And I superimpose over it, it will give me this first thing. I take this region and superimpose over it. The lambda and minus lambda will give you a neutral region, and this is your cutout section. The neutral region is the cutout section. So principle of superposition simply says that electric field will be the sum of the values of electric field due to different cases. Because these two cases combine together to give you this case. For this case, electric field was 0. But for this case, you see here it's minus lambda now. Minus lambda, so charge will be minus lambda dl. At this point, electric field will be towards the negative charge. Call it dE. If you write it as dE, the value will be k. Instead of charge, we'll write minus lambda dl upon the radius square, because distance between the point and the charge is r. So that will be minus k lambda dl upon r square. That is the value of E2, charge due to only this small portion. And the resultant value of electric field will be just k lambda dl upon r square. Negative sign means it is in this direction. That is the value of electric field. This was principle of superposition. We are imposing this on this. Here there was plus lambda, here there was minus lambda. And if I could overlap this, try to be imaginative, if I could overlap this, the lambda and minus lambda, they will overlap each other and give a neutral region. Neutral region is equivalent to the cutout section. These are smart ways to approach problems. So this is your origin, this is the x and y axis. And you have several charges in the region. For example, you have charge Q1 here. Let us first find the electric field due to a single charge at any point. So let us say this is at position R1 and your particle is at position, your point where you want to find the electric field, that is R2 vector. This is the point P where you want to find the electric field. And this is the position of charge, position vector of charge, where your charge is located. From Coulomb's law, you know that the direction of electric field will be along this line. We'll also make the arrow along this line. Call it from A to P. Charge is kept at point A. And you want to find the electric field at point P. So if you want to write the vector, let me call this as R vector. So electric field, only the magnitude if you want to write, it will be K, Q, call it only Q, upon R, this R vector, mod of R square. And if you want to write it in vector form, you also want to give it a direction. You simply need to find a unit vector along R cap, along the AP vector. Okay, so R vector is basically your AP vector, and you have a unit vector along AP vector. You can write it as R cap. R cap can be defined as AP vector divided by mod of AP vector. This is the formula for electric field in the basic form. And we'll use a little bit of more of vector quantities. From vectors, you know that OA vector plus AP vector equals to OP vector. See, vectors are like displacement. If you want to go from O to P, one thing is that you can go from O to P directly. If you go from O to P directly, you write it as OP vector. Another thing is that you can go from O to P taking this route, from O to A first and then A to P second. That gives you OP vector as OA plus AP. So from here you can write your AP vector is OP minus OA vector. And your OP vector is R2 vector. OA vector is R1 vector. So you can write your R cap as R2 vector. R cap was AP vector by mod of AP vector. AP vector is R2 vector minus R1 vector, and mod of AP vector is just R vector you can write, or mod of R2 vector minus R. You can put this R cap in here. You can put this R cap in here, and then we'll get something. E vector is 1 by 4 pi epsilon naught. Q by R cap is R2 vector minus R1 vector divided by mod of R square. And if you see here, this is just R2 minus R1 by mod of R vector. So this will give you mod of R vector cos square divided by mod of R. The final formula that we get, electric field is equal to 1 by 4 pi epsilon naught Q upon, this is mod of RQ into R2 vector minus R1 vector. This is a vector quantity. So this gives you formula in the vector form. 1 by 4 pi epsilon naught Q R2 vector minus R1 vector divided by mod of R2 minus R1 vector whole cube. This is your equation of electric field when you know the position vector of the point and at which you have to calculate the electric field. Here R2 vector, what was R2 vector? Position vector of point where you want to find electric field due to position vector of point where electric field is to be calculated. And R1 vector is position vector of the charge. We'll take up a simple problem to understand this. Let's suppose this is your XY axis and you have capital Q charge placed at the point 2, 3, and you want to find the value of this charge is Q. Charge is Q. You want to find the value of electric field at point P. Let us say it is at point 5, 7. So what you need to find? You need to find R2 vector minus R1 vector. That is your QP vector. Okay. So your R2 vector is the position vector of the electric point where you need to find the electric field. So that will be 5i cap plus 7j cap. And R1 vector is position vector of the charge. So position vector of the charge can be written as 2i cap plus 3j cap. To apply this formula, E vector equals to 1 by 4 pi epsilon naught q, value of q is q, r2 minus r1. If I need to calculate r2 minus r1, let me calculate it beforehand. That will be 5 plus 7j minus 2i plus 3j. That gives you 3i plus 4j. And let us also calculate mod of r2 minus r1. That will be root over 3 square plus 4 square. 3 3 is 9, 4 4 is 16, 9 plus 16 is 25, 25 root, that gives you 5. So kq upon r2 minus r1 vector is 3i plus 4j, whole thing divided by 5. Q. This will be the value of electric field. If you have the value of charges, you can of course calculate it exactly what is the value of electric field. Okay, any confusion in this? Go through the steps one by one. Don't write vector form of Coulomb's law. So now it will take very less time. You have the x and y axis. You have two charges q1 and q2. Let us say first charge is at point A, second charge is at point B. And you want to write the force on second charge due to the first charge. You know that it will be along this vector. And these are the position vectors, r1 vector. This you can write it as r2 vector. This is your r vector. R vector, to put it simply, is r2 minus r1. So force on charge particle 2 due to 1. This is force on q2 due to q1. That equals just multiplying this thing by q2. So 1 by 4 pi epsilon naught q1 q2 into r vector by mod of r q. Here r vector, you can put it from here. This is vector form of Coulomb's law. So two charges, when their position is given, you can find the force on first charge due to the second charge. Also, if you want to find force on q1 due to q2, now this can be easily found. You know that force on 1 due to 2 is negative of the force on 2 due to 1. Just write the negative sign and you will get the value of force on first particle due to the second particle. Did you say anything? The voice is not clear if you're saying something.
So are you talking to me?
Yeah, any student was saying something. The voice wasn't clear.
No, sir. Nobody was saying anything, as far as I know.
Okay. So this was when single point charge. You want to find electric field due to a single point charge. Then we can similarly write formula for electric field due to linear charge distribution. Electric field due to linear charge distribution. So now this time you have your x and y axis. The initial point, call it point A, is now a length, and the charge, well, the value of the charge will be lambda dA. If this line is linearly charged with lambda. So charge on this small region will be lambda times dl. And you want to find the electric field at point P. And let us write this as r vector. In very simple terms, you can write the electric field at point P. That will be 1 by 4 pi epsilon naught. Instead of q, you will write lambda dl. Instead of the vector, you can write this as r vector and divided by mod of r cube. But the charge is distributed over the whole length. So you would need to integrate. This whole integration will result in the final answer. Lambda dl upon r vector upon mod of r cube. This formula when charge is linearly distributed, then we can have surface charge distribution. Same thing. I already given an introduction on how you can find the magnitude of the charge. So suppose there is a surface and the whole surface is positively charged. And when there is a surface, you define sigma. Sigma is charge per unit area. So for a small region, call it dA, let us say the charge on it is dq. dq can be written as sigma times dA, because your sigma is dq by dA. If this sigma, you want to find the charge due to this charge particle at some point P, where this is your r vector, you can write the electric field due to this region. Small region is 1 by 4 pi epsilon naught. Instead of dq, you will write sigma dA. You will write sigma dA, and this is r vector whole divided by mod of r cube. Same formula, but instead of dq, we write sigma dA. And to find the electric field due to all the points on the surface, you use the integration sign. So this was linear charge distribution, this was surface charge distribution, and next is the volume charge distribution. This might seem a bit abstract. Don't worry, we'll be doing a set of problems. Of course, all of the problems in your book, we'll solve it one by one. And you'll be facing a lot of challenges in solving the book. The difficult ones we'll be discussing in the class. But the stronger you fight, the harder you fight, the stronger you become. Next is the volume. Suppose this is a region, a volume region, and it has charge per unit volume. Charge per unit volume is charge per unit volume dq by dV. And you have a small region. Again, you take a very small region. The small region, let us say this region has charge dq. Charge dq will be rho times dV. And you want to find electric field due to this charge at point P. Let's take this as a general vector, r vector. Again, electric field due to this point will be 1 by 4 pi epsilon naught integration of rho dV, that's the amount of charge dq, into r vector upon mod of r cube. These are the values of the formulas. And don't worry if you don't understand this. Just understand how we wrote the formula, and how we'll apply it. We'll still come to that. There's a still long way to understand how we are going to reach that point. Any questions over this? This is your x-axis, this is your y-axis. Let us say you have a charge at the origin and its value is 1 microcoulomb. You have to find electric field at point P, which is, let us say, as the coordinate as 3, 4 meters, of course. And you can take the value of K, that is 1 by 4 pi epsilon naught, as 9 into 10 raised to 9 Newton meter square per Coulomb square. Find, question is find electric field at point P. Find electric field at point P. Micro is 10 to the power minus 6 and 1 microcoulomb charge is placed here. Let us take 2 microcoulomb charge. Find the value of electric field at point P. So AP vector is OP vector minus OA vector. OP vector is 3I cap plus 4J cap. And OA vector, A vector is at origin itself. So A vector will be 0I cap plus 0J cap. That gives you 3I cap plus 4J cap as the AP vector. Then you can calculate mod of AP, put all those values in this equation, and come to this.
Pi cube.
Pi cube. So AP vector will be, that will be 5. And 1 by 4 pi epsilon naught is 9 into 10 to the power 9. This is 2 microcoulomb. That is 2 into 10 raised to minus 6. Micro is 10 raised to minus 6. AP vector is 3I cap plus 4J cap whole divided by 5. A little bit of calculation, 9 to the 18. 10 raised to 3 divided by 5 cube. 10 raised to 3 is basically 10 is to 10 into 10. So 10 cube by 5 cube. 10 by 5 cube. Eight into 2 cube is 8. Here it is Newton per Coulomb. One 44 into 3I cap plus 4J cap. We can write the final answer as 432I cap plus 576J cap Newton per Coulomb. So this gives you the value of electric field in the vector form. Any questions on this? Okay. Here there was a single charge. If suppose we have two charges, first charge is, let us say, Q1. Second charge is Q2. I'll give the value of Q1 as 5 microcoulomb and Q2 as minus 5 microcoulomb. And let us say you have to find the value of electric field at point P Its coordinates are 5, or give it as 4 comma 0. Coordinates of q1 is 0 comma plus 3, and for this the coordinate is 0 comma minus 3. Of course, the unit are in meters. Let me give this as 5 by 9 coulomb and minus 5 by 9 microcoulomb. And instead of meter, call this as centimeter. To solve this, you can just mark this point as A, mark this point as B, and use principle of superposition. Electric field due to net electric field will be electric field due to the first charge plus electric field due to the second charge. Try to find it out. Try to find the answer for this.